Taylor series. Taylor series centered at x equals c. F of x equals f of c plus first derivative of c times x minus c, plus the second derivative of c over 2 factorial times x minus c squared, and then we'd have the third derivative of c over 3 factorial times x minus c to the third, and so on. Now this is really over 0 factorial, and this is over 1 factorial, but both of those are 1. If c equals 0, the series is called a Maclaurin series. Find a Taylor series for f of x equals e to the 5x, centered at c equals 2. Find the first 4 non-zero terms and the general term. So we have f of x is equal to, we have e to the 5x, and when we evaluate this at 2, we get e to the 10th. Then the first derivative is 5e to the 5x, and that is 5e to the 10th. And then the second derivative is 25e to the 5x, and that's 25e to the 10th. And then the third derivative, and this would be the fourth non-zero term, is 125e to the 5x, and that's 125e to the 10th when we evaluate this at 2. So the Taylor series is going to be e to the 10th, and then plus 5e to the 10th, and we have times x minus 2, and then plus 25 e to the 10th over, that's going to be over 2 factorial, times x minus 2 squared, and then finally plus 125 e to the 10th over 3 factorial, times x minus 2 to the third, and then plus dot, dot, dot. Well, we can summarize this. We're going to go e equals, or we're going to sum from n equals 0 to infinity. And we have e to the 10th in every single one of them. So we have e to the 10th, and then times 5 to the n, and that's going to be over n factorial, times x minus 2 to the n. This one is called the power series, and we're going to find the Maclaurin series for this. So we're going to start with f of x, and this is really 1 minus x to the negative 1. And when we plug 0 in, we get 1 to the negative 1, which happens to be 1. And then f prime of x would be equal to negative 1 minus x to the negative 2, but then times negative 1, so that makes that positive. Then when we plug 0 in, we get 1 to the negative 2, which is 1. And then the second derivative is equal to, we have negative 2 times 1 minus x to the negative 3, but when we take this times negative 1, that becomes positive. So when we plug 0 in, we get 2. And then the third derivative is equal to negative 6 times 1 minus x to the negative 4, and then times negative 1, so that's positive again. So when we plug 0 in, we get 1 times 6, and that's 6. And then the fourth derivative, let's go one more. That's going to be equal to 24, 1 minus x to the negative. Of course, this is going to be negative 24, but then times negative 1. So when we plug 0 in, we get 24. Well, let's look at what the series is. We start out with 1, and then plus 1 times x, and we're centered at 0. And then we have plus 2, and then x squared, but that's over 2 factorial. And then plus 6x to the third, and that's over 3 factorial, which happens to be 6. And then we have plus 24x to the fourth over 4 factorial, which happens to be 24. And we have plus dot, dot, dot. Now this becomes 1 plus x squared plus x to the third plus x to the fourth plus keep on going. That's really why it's called the power series, because you just end up with all the powers of x. So let's we have n equals 0 to infinity of x to the n. Here we've plotted the power function right there, 1 over 1 minus x, and we've entered in a few terms of the power series. And here's that parabola, and this is actually 1 over 1 minus x right here, and then down over here. And notice that it only converges from negative 1 to 1. And if we put a whole bunch more terms, it's good between negative 1 and 1, but then starts to fail. And then if we plug in even more terms, This is an x to the 7th, and it's good from -1 to 1 and then starts to fail. So the convergence of this is only from -1 to 1. So we have the absolute value of x, wrong one, the absolute value of x, that's going to be less than or equal to 1. There's your convergence for the power series. In other words, it's good as long as x is between -1 and 1. There are 3 special Maclaurin series you must know. These are the series for e to the x, sine of x, and cosine of x. To derive a series for e to the x, we have f of x equals e to the x, f prime of x equals e to the x, f double prime of x equals e to the x. And if we're going to do Maclaurin series for these, e to the 0 equals 1. So this is 1, and this is 1, and then let's go the third derivative of x is e to the x also. And when we evaluate at 0, that's 1, and even the fourth derivative, we could keep doing this forever, we're going to get the exact same thing. So here's the series. We have 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and so on, plus x to the fourth over 4 factorial plus ... So here's the series. We have n equals 0 to infinity. We have x to the n over n factorial. Here we've plugged in a couple of terms of the series that represents the function, and here we have some convergence. We plug in a few more terms. We have more convergence, a wider convergence, and then if we plug in a whole bunch of terms of the series, it's converging even farther. So e to the x converges for all reals. It's not just -1 to 1. It converges everywhere. The more terms you plug in, the wider it's going to converge. To derive a series for sine of x, let's start with f of x equals sine of x. And when we evaluate this at 0, sine of 0 is 0. And then the first derivative is cosine of x, and cosine of 0 is 1. And then the second derivative is negative sine of x, which when we evaluate at 0 is 0. Third derivative is equal to negative cosine of x. Then when we evaluate this at 0, we get -1. The fourth derivative is going to be sine of x, and that is going to be 0. And we're right back to where we started. So fifth derivative is cosine of x, which is 1. So notice that the odd powers are Notice that the even powers are going to be 0, and the odd powers are going to alternate signs. So we start out with 0, and then we have plus 1x, and then we have plus 0x squared, and then minus x to the third over 3 factorial, and then we have 0 for 4, and then we have plus x to the fifth over 5 factorial, and we'd have minus x to the 7th over 7 factorial, and plus x to the 9th over 9 factorial, and we'd keep on going in that manner. So let's do the series. We have n equals 0 to infinity, and we need x to the 1, 3, 5, 7, 9. So that's x to the 2n. If we plug in 0, we get 0, so then we add 1. And then that's going to be over, 2n plus 1 factorial. Now, sine is an odd function. It is symmetric over the origin. So here's a graph of sine like this. So if you pick a point over here and then go through the origin, you're going to get a corresponding point. So since sine is an odd function, the odd powers are represented in the Taylor series, or in this is actually the Maclaurin series. But we also have to include, and we usually put this in front, but this is alternating signs. So since it alternates, we're just going to need this to be to the n, because we'll have positive and then negative and then positive and then negative. And sine converges for all reals, so its convergence is all reals. The more terms we put in, the more it's going to converge, the wider it's going to converge. To derive a series for cosine of x, we have f of x equals cosine, and the Maclaurin evaluation is 1. First derivative is negative sine, that's 0, and so on. You can pause the video and write these derivatives down if you'd like. But this starts with 1, and then minus. We'll have x squared over 2 factorial, and then plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and keep on going in that fashion. So let's get the summation for this. We have n equals 0 to infinity. And we actually want x to the 0, x to the 2, x to the 4. But first of all, alternates. So we have negative 1 to the n. And then we have x to the 2n over, and then we'll have over 2n factorial. Cosine converges for all reals. We can manipulate these three special series or any series we are given to find other series by using the following techniques. 1. We can substitute into the series. 2. We can multiply or divide the series by a constant and or a variable. 3. Add or subtract two series. And 4. We can differentiate or integrate a series. Example, find the Maclaurin series for f of x equals sine of x squared. So let's find the Maclaurin series, and we're going to start out with sine. So sine of x is equal to, this is an odd function, so we're going to have x to the first minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial, and so on. Well, now plugging x squared in for x is a replacement. So we have sine of x squared is equal to x squared minus x to squared to the third. So when we plug x squared into x to the third, we get x to the sixth. We multiply the powers. Well, now we have x to the sixth over 3 factorial, and then plus x to the 10th over 5 factorial, and then minus x to the 14th over 7 factorial, and keep on going in that fashion. So now we're going to sum this up with n equals 0 to infinity, and we notice how the powers are increasing by 4. Well, first of all, this alternates, so negative 1 to the n, and then we need x to these increase by 4, so that's going to be the slope of our little linear power. But if I plug 0 in, I get 0, and I want 2, so 4n plus 2, and this is going to be over. These are increasing by 2. These are the odds, so this is going to be 2n plus 1 factorial in the denominator. Find a Maclaurin series for f of x equals x cosine of x. Let's start out with cosine of x. Now that's an even function, so we'll have 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and so on. Well, now if we're going to take x times cosine of x, that's not a replacement, this is multiplication. So we're going to multiply all of these by x. We get x minus x to the third over 2 factorial, plus x to the fifth over 4 factorial, then minus x to the seventh over 6 factorial, and so on. So now we have n equals 0 to infinity, and these are increasing by 2. They're actually the odds, aren't they? So it's alternating signs. So we have negative 1 to the n, and then x to the 2n plus 1, and that's over. These are even, so on the bottom we have 2n factorial. Find a Maclaurin series for f of x equals e to the 2x. Well, e to the x is equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial, maybe one more, plus x to the fourth over 4 factorial. And e to the 2x is a replacement. We are replacing x with 2x. We have 1 plus 2x plus 4x squared over 2 factorial plus 8x to the third over 3 factorial, and then plus 16x to the third over, x to the fourth over 4 factorial. And let's sum this up. So we have n equals 0 to infinity of, we have 2 to the n, and then x to the n, and that's going to be over n factorial. Use your answer to A to find a Maclaurin series for the function h, given that h prime of x equals e to the 2x and h of 0 equals 3. So what we're saying is this function right here is actually h prime of x. It's h prime of x, and we're backing up to the original function. So to find h of x, we're going to integrate this, and when we have an indefinite integral, we have c. The integral of 1 is x, and then the integral of 2x is x squared. And then we're going to add 1 to this power. That's going to be x to the third times 4 over 3 times 2 factorial. and then plus x to the fourth times 8 over 4 times 3 factorial, then plus x to the fifth times 16 over 5 times 4 factorial, and keep on going in that fashion. Well, if h of 0 is equal to 3, that means when we plug zeros in for all of these x's, we get 0, and then c will equal 3. The function is 3 when we plug zeros in, so the constant's 3. H of x now is equal to 3 plus x plus. In order to get a nice pattern, we're going to cheat a little bit. We're going to take 2 times x squared, and we're going to divide by 2 factorial. That's 1, so we're allowed to do that. Then we have plus 4x to the third over 3 factorial, plus 8x to the fourth over 4 factorial, 3, 1 times 2 times 3 times 4, that's 4 factorial, plus 16x to the fifth over 5 factorial, and keep on going in that fashion. So let's sum this up. We have n equals 0 to infinity. Now the 3 kind of messes up the pattern, so we're going to put a 3 plus out here. And then we have x to the n plus 1 if we start at 0. And then that's going to be over n plus 1 factorial.